So let's talk a little bit about the agents, search reinforcement learning, and stochastic optimization. So the things that form the basics for the non-myopic decision making. So first of all, let's kind of consider why the non-myopic decision making is even necessary. The reason is very straightforward. So whenever we are doing something in the real economy, we start typically with some form of theory, either the computation, modeling, domain intuition, whatever. So the important thing is that the theorists can be pure theorists. Experimentalists cannot be a pure experimentalist because experimentalists always have to be a theorist on some level in order to be able to plan the experiment. So then we start with some materials discovery cycle, which includes synthesis, multiple characterizations. Then we move from material discovery to device prototypes. Then we go to the products. So once we go that, what happens is that here, our experiments are usually fairly shallow. So explore certain material space, explore certain processings, run the microscope in more efficient manner, and so on and so forth. Once we go for the device prototypes, and especially for making a product, our decision spaces become much, much larger. So for example, when people make batteries on the gigafactories, so the process has 24 steps. Each step have tens of the control parameters. So the decision space is enormous. And practically what happens is that the feedback times are very low. So when we're in the lab, we typically iterate very fast. When we build devices, the iterations are slower. When you build a product, the process can take years. For example, battery testing takes several months. And basically what that means is that when the dimensionality of search space is low and the feedback is fast, we can use database methods. Once we move into the situations when the decision-making is complicated and the feedback types are very low, we can no longer do that. So in other words, there is always a boundary above which myopic decision-making is impossible. So we cannot make decisions based on data only, simply because data takes forever to obtain, and we require a lot of that. So in this type of, so the things like Bayesian optimization loops that we considered, or agents or whatever, it's an attempt to isolate the part of this value creation chain for the certain level of times and feedback rates, and optimize a part, assuming that optimization of the part will improve the whole. So, but as I mentioned, in many cases, we cannot do the myopic decision-making, and then we have to operate in a more open-ended decision environment. So this is called multi-stage decision-making. So this is not a new field, so it has been explored by many scientists over the last 70, 80 years. And a lot of things that have been created in this field are relevant even now. For example, Kalman filtering, which is an example of the prerequisite for the open decision-making for the optimal control, was invented in the 60s. So Kalman filtering, as you can imagine, had the primary customer in terms of the people who used one rapidly moving object to intercept or destroy another rapidly moving object. So that's sort of very clear where this comes from. So same type of story that the Silicon Valley was built very rapidly, because that was the time of the when the ballistic missiles were developed. And once you have ballistic missiles, both sides started to think about the counter missiles. But the counter missile cannot have electronics based on the vacuum tubes, because vacuum tubes simply get destroyed during the launch. So despite the fact that the performance of semiconductor electronics at the beginning was fairly low compared to the vacuum tubes, you could put them in the Nike Ajax counter missiles and vacuum tubes, you cannot. So a lot of things go back to defense in some form. So anyway, another example of the control theory at that time comes from the people like Dmitry Bertsekas, who died a few days ago, from the Arizona State, who worked on the optimal control theory, from Bellman, who worked on the famous Bellman inequalities. The problem was that many of these fields were believed to be fairly narrow and isolated and kind of limited to specific types of systems. For example, optimal control of dynamic systems was very different from reinforcement learning, was very different from the dynamic programming. So now what happens is that many of these fields are coming together and start to use the common examples, which is both good and bad. Good because we can use it, bad because we need to understand the basic premise of these methods and how to use them in order to choose the right one. So very famous example from the field of reinforcement learning. So reinforcement learning is super popular. And one of the basic problems they want you to solve is the card pull problem. So you have a card that you can move and you need to balance a pull. So solving this type of problem by the reinforcement learning is highly suboptimal because this is an optimal control problem for the physical system. So it should be really solved by the model predictive control rather than anything else. So anyway, going back to the multi-stage decision-making, this is the field that was actively developed in the 80s and 90s, typically by people like Norvig and company. And the idea was, in all cases, the same. So you have a system that interacts with the external environment. The system has the inputs from sensors, cameras, GPS, and so on. The system can take action, which is steering, acceleration, control, and it has some goals, so something that it wants to accomplish. So notice that this setting is absolutely equivalent to the machine learning agent running the microscope, or for that matter, human running the microscope, because we have precepts. So we look at the screen and we see what happens. We have actions, so the knobs that we turn, which knob we select and how much we turn it, and we have a goal that we want to accomplish. So basically the problem of the non-myopic decision-making is equivalent to this problem of the agentic action. And by the way, if you follow what happens in the machine learning world and you see people working on these things like world models, whatever, kind of keep in mind that now they are done for real with the real computational firepower, but the concept and thinking behind of them is fairly old. And typically there is a strong benefit into going to the original sources and reading them, because when people do something first time, they have to deal with the high barrier of distrust from the community, which means that generally they do a much better job explaining what has to be done, why it has to be done, what is the value benefit, and so on. Now people can do a lot of things just saying that we are going to develop a $10 billion model. Nobody looks at why it is necessary in the first place. So good idea to combine. So anyway, when it goes to the decision making, it makes sense to sort of analyze what your environment is. So do you have full access to the environment, or you have to learn it? So for example, if you play computer games, you see the full game board. If you do something online or automated transport, then not. So is it deterministic? So do things happen deterministically, or there is a random component? So is it episodic, meaning you do it many times or only one time? Is the environment static? Is the process discrete? And so on and so forth. Obviously, the real world is inaccessible, stochastic, sequential, dynamic, and continuous, meaning the worst of the possibilities. Naturally, the way to deal with the real world problem is to try to freeze some of these degrees of freedom, because that makes the problem much, much more tractable. And then going back to agents, so this applies to universally agents, so in the sense of the ML system interacting with the outside world. So the agents, according to Norvig, has essentially four levels of complexity. So the most simple type of agent is what is called the reflex agent, or what we learned as the fixed policy environment. So the way it works, that there is an environment, so agent interact with this, but it doesn't have control over it. I mean, control only through actions. So that we learn the information about the environment, we get an idea of what the world is like now. A very important thing in this case is the choice of how we represent the world. So this is called a state variable in the decision theory. Basically, what we need to know about the world is only the aspect that is relevant to our decision making. Finding the right level of the representation is a complex task, because if you choose your list of the representation too broad, you cover everything you need and what you don't need, and nuisance parameters are not good. You can neither control them, nor, and they are kind of deleterious to your predictive models. If you choose things too narrow, then you can kind of throw out relevant information together with the correct one. So practically, it's always a choice of how you represent the world. Do you take an image, or do you take a list of atomic coordinates, or do you take a histogram of possible atomic configurations? So then, however, when it comes to the reflex agents, the idea is very simple, that you have a figure of the world, you have the fixed policy, which is condition action rule, and then you take an action, then the action is passed to the universe. So when you have the automated tool with the prescribed fixed policy experiment, that's a reflex agent type of setup. So it doesn't have to be this way. So you also can have the more complex version of the agent. Rid of this thing. Which is the agent with the state. So in this case, what happens is that you still get an idea about what the world is now based on sensors, but you also try to predict a step forward. So what type of outcome is your action likely to do? And based on the output of this action, you choose what action to take. So notice very important thing, that in this level, we try to predict the outcome of action rather than just taking an action because somebody told us to do that. So the good example here would be trying to repair the something using the manual. So you always want to analyze what would be the outcome of the action that you take. So the reward-based optimization that I've shown, so everything related to Bayesian optimization or deep kernel learning, this is a goal-based agent. So in this case, rather than taking an action, we define what is that we want to accomplish, and we try to kind of learn how to accomplish this goal. So this is how it works. You get an idea of the state of the system, so what the world is now. You predict what it will be if I do the action A. So the DKL or Bayesian Gaussian process builds the surrogate model. What would be the outcome if I do something? And then depending on the goal, the function that you want to maximize, you choose what action you are going to take. So this is where we are now with the Bayesian optimization type of workflows. And the most complex example of agents is the utility-based agent. So this one is a little bit more subtle. So it looks like this. So we take an action, we estimate what would be the outcome of the action, what will happen to the world if the action is taken. And then we define the utility, which is roughly how happy will I be in this state. So this is actually adding the fact that it basically has the element of somehow formulating the reward function. So in the previous version of the agent, reward function was formulated as the goal. In this case, it starts to formulate what is the intrinsic measure of success that I will have in this future state. So it's kind of getting fairly close to the way that humans operate, because sometimes I will be happy if I write a paper, and sometimes I will be happy if I have a beer. So the question is, these are kind of not comparable, which basically means that my selection is driven by the utility consideration, not by a fixed reward function. Now, so why does agents matter? So agent shows you what type of action, how you can make decision about what action to take, depending on the state you are and the information that you get. Once you move once you define the way that you can take actions, then you immediately have questions about how do you define the sequence of actions. And this is when the agent problem start to connect to the search problem. So what I mean by that, so notice that there is a little bit of things that on the one hand are almost self-evident, but at the same time unnecessary. So the assumption is that we can define the state of the system that's amenable to the object. This state is one instance of the set of the possible states. We assume that this set of states is closed, meaning that the actions that we take bring us to the new states that are part of this global state of states. So, for example, if I walk around the floor, my state is two-dimensional, but I'm not going to move magically in the third dimension. At least unless Gerd put something special in the drink that he gave us. So the idea is that the possible states are the states that I can reach from the possible action, and generally we need to kind of make sure that this state is complete and it's closed under the actions, meaning that I can explore the state space by the actions that I have, and that the actions that I can take are not going to bring me to the state that's not a part of this set of states. So practically, it's kind of mathematized in most experimental scenarios. This type of conditions satisfied automatically if we know what we are doing. So for us, it's kind of, we can fall back on the intuition. Then once we do that, we basically can define our non-myopic decision-making as the search in the space of the possible actions, where we make one step, take one action, we end up in state. We choose what action to take, we end up in a different state, and then we want to move from this sequence of states iteratively until we get to our goal. So then our experiment or action, sequence of action becomes the path through the space of possible actions of states, where each action brings us from state to state. And that basically start to map one-to-one to the concept of search. So very famous concept that folks in the computer science have explored basically forever. So we can search in the space of the possible states, and the sequence of actions can be basically represented as the search tree. So the very famous example here is the sort of traveling travel type of problems. So if you start with one city and then you have a choice which train to take, your first action is direction, what is the next city, a third, and so on and so forth. So this is a classical tree decision process. So once you define and generally, sort of, we can say that anything that you can practically do in the laboratory or anything that you can practically do with a single instrument would be a search in the space of the possible action, so almost by definition. In our case, we know that the closure condition simply comes from the fact that we deal with the real physical world and not the abstract mathematical concept, so everything would be well behaved. And therefore, our problem is formulated: how do we create a sequence of actions that brings us from where we are to the goal where we want to be in the most efficient way? So the problem here is that anything that's related with the sequential decision-making leads to the exponential growth of this search tree. So if we have 4 possible actions, that at the first step we have 4 choices, second step we have 16, then we have 16 times 4, 64, and so on and so forth. So if we try to solve this type of problem through the direct optimization, we start to have to optimize over the spaces 64 and so on and so forth. That's kind of intractable. We cannot do that. So we need to have a much more effective ways in order to solve this type of search problem. So how can we do that? So the basic strategies for doing it can be initially separated into the informed versus uninformed search. So uninformed is essentially forms of the brute force exploration. So informed search strategies use the information about the problem. So let me show you brief examples how it can be done. So the uninformed search can be the breadth first search. So basically, if you have 4 possible actions in the first state, you explore the outcome of these 4 actions. So you repeat experiment 4 times. And then for each action in the second layer of decision-making, you kind of explore the outcomes of the actions in this case. So you kind of go through your decision tree layer by layer, and obviously the number of candidates to explore goes exponentially. The modification of this breadth first search is the uniform cost search. So then rather than going by layers, you also take into account the cost of each action. So if the action is expensive, you defer it for the future. If the actions are cheap, you kind of prioritize them. So another example is the depth first search. So in this case, rather than explore your decision tree layer by layer, you kind of go all the way to the end for one of the branches, then you go back and go the other branch. So kind of choose your poison. The problem is that none of these strategies is particularly efficient. So you always end up having very many explored candidates. And for experimental scenarios, it's just not feasible. We cannot do that. So experiments generally can be run only once. So what is the alternative? So the alternative is what is called the heuristic search. So heuristic search is something that is already practically used. So for example, A-star algorithm that I will show, or Markov chain decision trees that has been used for mu0 or for AlphaGo. These are the example of the heuristic searches. So how does it work? So the idea about the heuristic search is that you have a search tree, but what you also have is the heuristic function. So for each state in the search tree, you should be able to estimate how far is your target. It doesn't have to be precise, but it has to be an optimistic estimate. So this heuristic function has to represent an estimate of the cost of the path from the given node to the closest goal state. So it's not true answer, but an estimate. If you are at the goal state, meaning if you reach your goal, then it should be 0. And this good heuristic basically allows you to find the solution much more efficiently. So the typical example of this type of search is the A-star algorithm. So the A-star does the following thing. It says that I want to get to the goal, and I estimate my cost, estimated cost to complete the path based on the cost to this moment. So this is how much investment I already made, plus the estimated cost to the goal. So this is what I've done. This is what I estimate remains to be done. And this is the criteria based on which I select what action to take. So the interesting thing here is that the heuristic function should always be optimistic. So it should underestimate the true cost. It's actually very interesting, and that's kind of a place where the machine learning and everyday life comes together. So if you're optimist, you generally can get things done. If you're a pessimist, chances are that you will never get things done because you will get trapped and kind of feeling miserable. So the simplest example, this heuristic function is very easy to illustrate for the search problems. So for example, if I choose how to get from this point to this point, I can estimate the cost of movement to the new location. And then I can, as the heuristic, I will estimate what is the direct line distance from the point that I select to the target point, which is straight line rather than travel distance. And obviously, whenever you use things like Google Maps or whatever, that's exactly how they do it, right? So if you want to travel from here to some specific place in San Francisco, you are not going to explore all possible paths from here to San Francisco because there are too many of them. Even the number of paths over Knoxville is kind of tremendously large. But your heuristic function is the minimization of the total distance from here to San Francisco, which basically tells you that taking I-40 and travel to the east, to the west is a good idea, and taking I-40 and travel to the west is a bad idea because it brings you to the opposite direction. So how we build these heuristic functions is a complicated part. And notice that one of the primary things that I was bringing up is that human input matters. So human input matters is the reward functions because that's how we define what to do. Parenthetically, that's the reason why I really don't think that AI is going to do our jobs, because they don't have any intrinsic reward functions, so they come from us. Either they come as formulated policies or low-level reward functions or high-level reward functions, but it's still human-driven. The second thing that is very often human-driven is the development of the heuristic functions, because there is no single right heuristic function. They actually require quite some creativity to build. Historically, for things like playing computer games and so on, the heuristic functions have been learned either from games realized on the slower, smaller fields, when you reduce type of the system in order to learn the general way that it operates, or heuristic functions came from the games where you reduce the number of constraints. So then gives rise to something like admissible heuristics. For example, for the puzzle where you have to move tiles, you can reduce some of the constraint on the available moves, and that gives you some form of heuristic that can be useful. So the problem is that in experimental world, we will have to do that. So, for example, in the synthesis problems, very often if the color of the solution is wrong, that means that the wrong reaction happened. You don't need to go to the detailed analysis to know that things didn't work out. In microscopy, if we run the experiment, we come to the lab and the pressure in the column is 10-3, that's probably not a good day to run the experiment as well. When it comes to the kind of equipment works, but we don't know whether it is right sample, I mean, all of us make decisions about it. So it's the way to construct a heuristic function is just think about the last several experimental campaigns you run on the instrument. If you have the feeling that you knew whether things are going to work out or not on this particular day, try to understand why. If you are able to formulate what is that about that they made you make a decision to stop or to continue, that means that you start to put your finger on identifying the proper heuristic for this experiment. Make sense? But as I said, for the time being, we are not anywhere else. We are not, that's not the field that has seen any kind of development. So one of the very important ways that both us and several other groups and communities start to explore is the use of the digital twin for the open decision making. So what's the idea here? So remember that the experiment can be run only once. So when we run a second time, it's a different experiment. So any type of decision making or creation of the rollout function, which is or heuristic function, requires from us the being able to predict the possible outcome of either next step or the whole experimental campaign, given what we already have now. So it looks like the way it can be done in a systematic, how we can do it in the systematic way, if we formalize our instrument and our sample as the efficient digital twin, meaning the system that contains the relevant information about the sample and about the instrument. So a single digital twin is not enough, because if you deal with a nuclear reactor or airplane or the bridge, we need just one digital twin, because we want to predict the behavior of this structure in time. When we deal with scientific instrumentation, we need to predict what would be the result of the measurement by microscope on the sample, which means that we need to have a digital twin of the microscope that can predict how it will interact and what type of results it will give on all the samples, and the digital twin of the sample that contains all the information about the sample that is sufficient for the double digital twin to predict what would be the results of the joint operation. So then if we try to kind of marry the search concept to the idea of the predictive model predictive control, we get with architecture something like this. So we need to have either human or machine learning scientist that proposes the experiment and proposes what actions to take. We have the digital twin for the material and instrument that will predict the outcomes of the possible actions before they're taken. So ideally, they predict both the outcome and uncertainty and risk. Depending on what we want to do, we pass the uncertainty and prediction to our experimental planner, and then it can use the same type of acquisition function in order to make the next step. We can look at the risk, and based on the risk, we can decide that I can take this action or I should not take this action. So simplest example, if I image the soft material with a specific probe and AFM, if I change the sample from soft to hard while keeping the same imaging parameter, I will probably destroy my probe, which basically means that my digital twin for the instrument combined with the digital twin for the sample should predict that the interaction forces would be dangerous, so I really don't want to start there. So if we can predict the next step, at least theoretically possible to make the rollout, so to have the completion heuristic. But again, so we still need to find out how well this type of concept works. So kind of that's one direction. So another direction that is very useful to know about, and you probably encounter many times, is the concept of the reinforcement learning. So for maybe last 8 years, reinforcement learning was one of the most hot topics in the field of ML. I have reviewed tremendous number of proposals where people said that we are going to use the reinforcement learning to solve problem A, B, and C or not. At the same time, I have not seen any published paper when the reinforcement learning was in fact used for anything useful. So this kind of brings the situation when it's a good idea to understand why and what reinforcement learning is, to know when to use it and when not to use it. So generally, reinforcement learning is a very interesting field that kind of lays on the intersection between the fields like operations research, so supply chain optimization, what's not, optimal control, so optimal control is purely dynamic field, and RL. So they have a lot of similarities in terms of what they want to accomplish and type of objects that they deal with. So the starting point for the reinforcement learning is the non-myopic decision-making algorithm. However, it is the decision-making algorithm that requires two foundational components. One component is the definition of the rewards, and I will illustrate you why it matters. The second component that matters is that your system needs to be represented as the Markov process, and that also brings certain constraints. So let me first illustrate what the rewards do, and second, what is the Markov decision process is. So imagine that you have, typically the reinforcement learning starts with problems like this one. It's called the grid world. So imagine that you have a robot in the room. So the robot, this is the wall, so robot cannot get here. A robot wants to get to this point. This is exit out of the room, so this is win. This is the robot doesn't want to get here because this is also the game over, but with the negative outcome. Let's say this is a trap and robot dies here. So what the robot wants to do is to get from this point to this point, and it absolutely doesn't want to get to this point to this point. Now, it's very obvious that this is not is a non-myopic decision-making, right? Because if you move from this point to this point, you are not over, right? You just need to make a next step. So you cannot optimize this step. You need to somehow optimize the whole system. So even for a very small system like this, optimization in the full configuration space is impossible because the number of steps that you can take is kind of significant. And more importantly, if you tell me that, okay, in this case, we have only something like 2 to the power, whatever, 15 possible trajectories, we sure can find the best one. it's very easy to throw the monkey wrench into the logic and say that, look, how about my robot is not perfectly controlled? For example, if I tell it to move up, then it moves up 80% of time, but 10% of time it moves to the left or to the right. So that's called the slippery ice world. Basically, it means that you can tell it what to do, but the outcome can be slightly different. So why does the reward matter? So let's assume that we want to find the best strategy to achieve the maximum reward. So strategy means finding policy. So policy in this case means that for each position of the robot, I want to provide the matrix which gives an optimal action. So in this type of problems, the policy can be shown as the collection of the arrows with a different orientation. And that's what the policy is. So if you are here, then the policy tells you to move here. If you are here, policy tells you to move here. So what we want to do is, given the rewards, we want to learn the policy. Rewards are what we give to the system. Policy is how the system to respond. So it turns out that for the condition that I've shown, that we have reward +1 here, reward -1 here, and then each step cost us 400. The optimal policy is like this, right? This makes perfect sense. So I want to, if I'm here, I want to go like this. If I'm here, I want to go like this. If I'm here, I want to go like this. Now, a very interesting question. So why not move like this? Why is this arrow oriented this direction and not this direction? So any thoughts about it?
It's yeah, but 10%.
Exactly. You're absolutely right. So this is because if we are here, we can end up being here because of the sliding thing, and therefore it is much safer to do things like this way. So what we can do is we can say that, you know what, how about we experiment with the cost of taking a move? And then we get a very interesting result. So if we take the cost of each step -2, then look what happens. Open obvious policy is that our robot wants to commit a suicide. So why does it want to do it? Because the life is so difficult that each step in this world costs it -2, and killing itself costs -1. Of course, it wants to kill itself as quickly as possible. So if the reward for each step is -0.1, then the robot wants to go like this. Notice that now it takes the risk to go around this one simply because there is a price for a fairly high price staying inside this system. If our reward for each step is -0.4, then it wants to minimize the risk and go around this because it's cheaper. And then if it is -0.1, so then it will be very very conservative. So if it is here, it wants to kind of pull itself into the wall because staying inside doesn't cost it much. And basically it waits for this 10% that will either bring it here or here. If it is brought here, then it go to the +1. If it is here, then it will try to run away from this part of hole, from this end state. And then, of course, if we make the reward for each step being +1, so the longer it stays inside, the more reward it accumulates. In this case, the robot really doesn't want to add to the terminal state at all. You see, it kind of tries to go away from the end and it wants to live forever. So it's very easy to rationalize. And what it basically illustrates is that for very, very simple scenarios, when the rewards, two of the rewards are more or less native, like +1, -1, like a normalization function, depending on what price we put on the cost of step, we have fundamentally different behavior. So this is actually the great problem, because one of the things that I did for my class is I tried to ask people to classify the possible policies depending on the reward, and it turned out that there are many more of them that I showed. So even such a simple system has multiple possible behaviors depending on how we define the rewards. So as you can imagine, if we try to use this type of decision-making for the experiment, we actually have to be cognizant of this fact, because depending on how we define the rewards, our decision-making agents will behave very, very differently. So the second part of the reinforcement learn, the important thing, however, is that when we run the experiment, the good thing is that many of this type of costs are clear, simply because if I use the instrument, I actually can calculate what is the cost of each step, because I know how much money I pay for an hour of instrument use from my account. So the cost I would know. What is the problem in experiment is typically the value. So here, we know the cost of the positive ending and cost of negative ending, but we don't know the cost of step. It's kind of set somewhat arbitrary. But in the real experimental world, we know the cost of step, but we don't know the value of the final outcome. That's one is something that we need to explore. So the second thing that we need to know about the reinforcement learning is what is the Markov decision process. So the way that it is often formalized is, you say you have an agent, you have environment, the agent takes an action, and the environment emits the reward and brings the agent to a new state. So what it means is that we need to have a set of states, set of actions, and the initial state. So this one is more or less obvious. So this one is more or less obvious. This is limited by our hardware. Set of states of the environment, this is simple only in the textbook. So practically, we need to define how we define the state in the simplest way possible. We already encountered it in a case of the deep kernel learning, because you can say that our state is the position of the probe on the screen, and that one is not very useful. Or our state would be the local microstructure, which is encoded as the latent variable of the deep kernel learning. That one is much more useful. So unfortunately, defining the right states, by now it is something like 80% of the job. So the second thing that we need to know is the transition model. So transition model is fairly complicated. So again, as well, so we know how to define it very well for the mechanical system. This is just differential equations of motion. For all other states, we have to learn. For all other systems, we actually have to learn what it is. But the typical assumption of the RL is that the transition model can be either defined or learned, and the reward function is specified. So once both of those happen, then we can define the goal, which is maximize the cumulative reward. And then what we want to learn is the policy. So policy is how you choose the action based on the state. So that's what the policy is. So defining states is relatively easy for systems with the discrete descriptors. So for example, if we want to define the state of the human interaction, we can say that, hey, I can work on the computer in my office, I can be at home, I can drink coffee, I can have a chat. So these are the possible states that represent human action. So notice that in this case, we have really simplified these things. We basically reduced all the possible things that human can do to only 4 types of activity. So this is the first step in setting up the Markov process. So the second step on setting up the Markov process is to introduce the probability. So let's assume that we check the state of person every 10 minutes. And if we check the state of person every 10 minutes, then we can define that if the person is working on the computer now, then in 10 minutes, with a probability of 50%, it will still work on the computer. If the person drinks coffee now, then with the probability 10%, it will keep drinking coffee in the next 10 minutes. But with probability 70%, the person will talk to somebody else. So if the person talks to someone else, with the next 10 minutes is going to keep talking to someone else. With a probability of 30%, it will stop talking and move to work on the computer, and so on and so forth. See what goes on, right? So here we did two things. We defined states and we defined the transition probabilities. And for continuous process, we said that this is a probability per certain amount of time. So what you have here is the example of the Markov process. So where the state of the system is determined by the previous state with some probability matrix and nothing else. So notice that if we are in this state, whether we will move to this state, or this state, does not depend on the history. It depends only on the current state of the system. So this is very important. This is called the Markov property. General reinforcement learning applies if and only if this Markov properties is fulfilled. Practically, that also means that you need to be very judicious choosing the states correctly, because sometimes if what you are doing now or the outcome of the action depends on the previous state and the state before it, the way to deal with the system is to join the previous state and the state before it in one global state. So that's kind of an art of the state building. And then the idea of the Markov process with the reward is that once you move between the states, you also get some reward from it. So for example, if you work at the computer and you keep working, you get reward of 5. If you work on the computer, but you go to chat with someone, the reward is -3. And if you are chatting with someone and keep doing it, the reward will be -1 per each 10 minutes. So obviously, if you're drinking coffee and keep drinking it, the reward in this case is positive, but nonetheless, it's a good idea to move from coffee to working on computer. The reward is 3. So once you have this type of things, this is the full setting of the Markov decision process with the rewards. The good thing is that a lot of problems in the world can be kind of approximated in this level. There is a lot of tweak parameters. The rewards have to come from somewhere. So obviously, when you're a 2-year-old at the daycare, the reward comes from the whatever people who run the room. So the reward is kind of large. When you're an undergraduate student or graduate student or whatever, the reward tends to be intrinsic, right? So nobody is going to watch over you and say, hey, you need to go to drink coffee or something like that. But this is the strengths and the limitation of the reinforcement learning, that state needs to be defined, the transition probabilities have to be defined, and the rewards have to come from somewhere. That being said, once it is done, once we have the transition probabilities, reward policies, we can actually define the state value functions. So the state value function would be, if I start in this state and keep moving along this, keep getting action, what is the long-term benefit? Not the benefit of the next step, the benefit of keep doing it over and over again. See the difference, right? So for the robot, the reward for moving from one position to another position was always constant, but ultimately it wants to get out or it will die. So in this case, what matters is the value of the state is not what the immediate reward from going from this state to whatever state. It's the value of being the state for a long time and follow the dynamics determined by this Markov process. So, this is what is the state value function is. And the action value function is basically a combined thing. It's what is the value of taking action A in the state S. So what type of rewards do we have to deal with? So generally, there is a little bit of subtlety whether you keep doing things only once or it is a long episode. So for finite horizon activities, like you have finite number of steps, you can calculate the additive rewards. Like if you want to calculate what's the best thing you can do within the day, you know that the number of 10-minute intervals within the day is 132, whatever. So that's your finite horizon. If you keep doing things over and over again, it's necessary to introduce the discount factor, which basically means that the immediate rewards matter more then rewards far in the future. And typically the way it is done is by introducing some coefficient gamma that decays with time. So practically you can estimate this gamma based on your total experimental campaign length. For example, if you have 100 iterations of the experiment, you can set gamma to 0.99. If you have 10 steps, you can set it to 0.9. So 1 over 1 minus gamma is roughly proportional to the total experiment length. And basically then these ideas of value that we discussed in the context of the bandits apply here as well. So the value of the state is the expected return if you are in this state and you follow the certain policy. So the state action value, if you start in the action S, perform action A, and then you keep following policy till the end of the experiment. That's your state action value here. So the way that their policies, values, and actions are connected is through the Bellman equation. So generally, if you see it first time and you feel that you don't understand anything, that's kind of normal. I looked at it for several years before I start to understand something. But generally, the meaning is very, very simple. So basically what this says is the value of the state under policy. So notice that it's always under policy because the state does not have intrinsic value at all. It has intrinsic value only if we define what are we going to do in the state. So the value of the state under policy is the sum of all possible actions of the probabilities of moving from state S to S prime, rewards on moving from state from S prime, plus gamma, the value of the state S prime. So the interesting thing here is that in some sense what we say is that the value of the state now depends in this way on the value of the state where we end up being. So you see, that's a kind of thing, or that's what's great about what Bellman did, and that also makes it difficult to understand, because the state that I am now, the value of the state that I am now depends on the value of the state in which I will be in the future if I take this action. But the value of the state in the future where I take the action depends on the value of the states further in the future. So the whole idea about the reinforcement learning is to be able to go to this future and then back propagate this value. That's why it is kind of difficult. So there are good news, and this good news is the reason why people are doing this type of stuff in the first place. So the first good news is that there is, in fact, it was indeed proven by Bellman that there is a set of optimal policies, basically meaning that of all possible policies, given the reward and given the Markov decision process, there is one that is better than everything else. This, by the way, is great because it tells you that there is a best solution and there's only one. That's already great. That's when mathematicians celebrate. This is also the problem when the engineers kind of got desperate, because if somebody tells you that there is a best solution and only one, then you realize that you're a poor schmuck who actually has to find it somehow. So there is a second thing that, interestingly, this optimal equation, optimal policy corresponds to the known optimal value function. Then you know exactly what the value of the state you are in. And if we know our rewards, states, and the transition matrices, there is a way to basically solve this system. That's a great news. It means that not only there is a best solution, but the best solution can be found in the finite number of steps. And that's great, because then if you went through all the kind of nightmare of defining states, transitions, actions, and rewards, you know that you will be able to get the solution because somebody somewhere, or I mean somebody somewhere meaning being Bellman, Bersikas, and so on, already figure out how to do it for you. That's a great news. The way that it is done is there are two strategies. One is the called value iteration. So basically the way you do it is that you define the value of all states being 0, and then you iteratively update the value for each state using the Bellman equation. So you basically start with the 0 value, and then you run this type of update. Notice that this is a nonlinear equation because you have max over argmax over actions, and therefore you have to do it iteratively rather than solving a linear equation. So you continue it until the value of the states converge. It's very easy to realize it for the frozen world type of environments. You just kind of see how the evolution of the policy happens. Basically, if you decide to play with this type of things, my advice is figure out the way how you represent the policy, meaning actions and the possible states, and then run it as the movie. It's actually very beautiful to see how things evolved. Even for simple problems like allocation of resources, the final movies that you get are absolutely spectacular. And then once you have the values for each state, you basically can extract the policy simply as this type of equation. So another way is called policy iteration. So policy iteration alternates between evaluation and improvement. So given the policy, you compute the value function. So if the policy is known, then the value function can be solved either iteratively or it is a linear equation. And then once you do that, you improve the policy. So you improve the policy by choosing the action that gives you the argmax, then it becomes nonlinear. And of course, stop condition is the same. So the good news is that, and practically both of them work. There may be a discussion about under which scenarios one is slightly better than the others, but generally for our applications, either is good enough. So what's the problem? So what's the good news, what's the bad news? So the good news is that if we have transition probability and rewards known, then the problem is solvable. That's great. The problem is that very often we deal with the scenarios where the world is not known. So in other words, you're in the state in action, but you don't know the transition probabilities, and you don't know the reward unless you take an action at least one time. So this becomes an exploitation problem, same as type of exploitation as for the Bayesian optimization. The problem is that in this case, we don't try to optimize the immediate reward in the myopic way. We try to optimize the reward of the long-term process. Unfortunately, there is no way to do it without collecting large amounts of data. So simply because some of your experiment will chart the world and some of it will try to optimize your conditions. And that's the reason why the reinforcement learning is almost unlimited field, because the number of ways it can be done is very, very, very large. So the reinforcement learning strategies are very much dependent on what is the system. So if you have a tabular system like the grid world or tic-tac-toe game, you use one type of approaches. If you have the system with the continuous action space, theoretically, you can use something like, there is a whole alphabetic soup of the methods, most of which I don't really remember, but there are all kinds of gradient learning, proximal optimization, and so on. There are multiple ways how the reinforcement learning can build the model. So this is called the kind of actor-critic methods or model-based reinforcement learning and so on and so forth. Practically, my advice is define the problem in the simplest way. So people who build reinforcement learning operate in the world when the computation is cheap. The number of the repeated computational experiments is almost unlimited. And they're used to having large volumes of data. There can be a scenario which something like this happens in our experimental world. This is not very likely. So practically, our tools are bandits. Just imagine how cool it is to give a conference on the talk at the conference saying, "I built a bandit." So kind of wearing the eye patch as well to kind of stay in the style. Our tools are things like the Bayesian optimization or myopic problems, our tools are model predictive controls and the digital twins, so something that give us an opportunity to make a theory-based rollout. Reinforcement learning is a great thing to know about, but there are very few problems where it is useful.